Hey everybody, this video lesson is entitled Electromagnetic Energy and the Effects that it has on Molecules. This particular learning objective from the course exam and description is 3.11, and it talks about the explanation of the relationship between the region of the electromagnetic spectrum and the types of molecular transitions that may occur depending on the energy and the wavelength of the light or the energy of the photon that a molecule would encounter. Truth be told, this is the first time this has been on the AP test. In fact, I've never seen this before this year. They added this when they did the minor rewrite to the course exam and description here just this year, which is why I'm adding it into my loose end topics. The Wayback Machine to the beginning of the school year when we talked about the electromagnetic spectrum. I introduced you to two formulas that can then be combined into one formula. Each formula is utilized a little bit differently. The first one was this one, and c is the speed of light, which is a constant value. It's 3 times 10 to the 8th meters per second. And that's equal to the wavelength of the electromagnetic radiation times the frequency of the electromagnetic radiation. And remember, these two are inverse of one another. As the wavelength goes up, the frequency goes down. As the frequency goes up, the wavelength goes down. This formula would be utilized, say, if you knew the frequency of the radiation and you were trying to figure out what wavelength it was, and vice versa. The second formula that I talked about back in that chapter was this one, and it's E is equal to H times V, or frequency. E is the energy of a photon, H is Planck's constant, and V is the frequency of the electromagnetic radiation. Now, the reason we have two formulas, if you remember, is that because electromagnetic radiation sometimes acts as a wave and sometimes it acts as a particle. And the formula on top is utilized when you're thinking about energy acting as a wave, hence wavelength. But down here, when you're thinking about energy as a photon, then you don't have a wavelength, you have a frequency, but not a wavelength, which is why we need the second formula, which talks about electromagnetic radiation in the form of a photon or a particle. We talked about the E, or the energy of the photon, when we talked about how atoms, and specifically electrons around atoms, can absorb a photon of a specific energy, and once it's absorbed that energy, it can promote its electron to an increased energy level, and then once it comes back down to its ground state, or its more stable state, it will emit a photon of light in a particular color. That color can be associated with a particular wavelength. So we need to combine these two formulas together to be able to relate energy of a photon and the wavelength of the light that it emits. So if you take this first one and you solve it for frequency, what you have is frequency is equal to speed of light over wavelength. Now I can substitute it in here to the second one and combine, and what you have is E is equal to H times C over wavelength. And now I have a formula that combines the first two, number 1 and number 2, into formula number 3. And now I can associate the energy of a photon with a wavelength of light that would be seen if that energy fell in the visible spectrum, or the wavelength of some electromagnetic radiation if it didn't fall in the visible spectrum. And all of this math now boils down to this. When a molecule or an atom encounters electromagnetic radiation of a different energy, it behaves depending on the amount or strength of that energy of the electromagnetic radiation. Not all radiations make an atom or a molecule behave the same. And this essential knowledge over here in this blue box helps break down the different types of electromagnetic radiation and the effects that it has on different molecules, or in C's part, the electrons in an atom. So let's say a molecule absorbs energy that comes in the similar wavelength as a microwave. So the energy coming in is microwave energy, and the energy associated with that could be calculated. If we knew the wavelength, we could calculate the energy. The microwave energy would have an effect on the molecule. And what microwave radiation does is it causes molecules to rotate. So in other words, a molecule will absorb energy that is associated with the wavelength of energy in the microwave region of the electromagnetic spectrum, and it'll cause that molecule to spin and rotate. This is the whole premise behind the microwave oven. How does a microwave heat up your food? Well, what it does is it runs electromagnetic radiation through your food at a microwave level, and the microwaves that are being sent through your food are basically causing the water molecules to spin in place, and that spinning causes the food to heat up. Your food is constantly bombarded by microwaves, and the water molecules continue to spin in place. And not just the water molecules, but all the molecules that make up the food spin in place. Now, infrared radiation, as you move further to the left, closer to the visible spectrum, you're getting higher energy, you're getting higher frequency, or lower wavelength. And in this region, if a molecule absorbs electromagnetic radiation in the infrared, which is very possible if it's coming from like the sun, for example, how does the sun heat up the earth? Well, the sun heats up the earth by sending infrared radiation, and that infrared radiation causes molecules to vibrate. Microwaves will cause molecules to rotate. Infrared will cause molecules to vibrate, not spin in place, but just wiggle back and forth. Both of these would result in the matter heating up. Because if temperature is a measure of the average kinetic energy of a sample of substance, then rotating molecules for sure, and even vibrating molecules, would result in an increase in temperature. Now, once you get to ultraviolet and the visible spectrum, which is located a little bit higher energy than infrared and a little bit shorter wavelength, you no longer contribute to the motion of the molecules, whether it be spinning or vibrating, but this type of electromagnetic radiation is associated with electrons being promoted to an increased energy level and then returning to their ground state and emitting energy. So ultraviolet and visible can only move electrons. It can't move molecules, only electrons. So in summary, the different types of electromagnetic radiation have different effects on a molecule. Microwaves cause the molecule to rotate. Infrared radiation cause the molecule to vibrate in place. And visible and ultraviolet radiation can only move electrons on atoms or molecules, but not the actual molecules themselves. The reason you care about this third formula is that you will probably be delivering the electromagnetic radiation in the form of a photon at a specific energy, and you'd be expected to figure out what wavelength of light or what wavelength of the electromagnetic spectrum that energy is associated with, and then apply that to one of these three situations. Is that energy a photon in the microwave area where it's rotating, or if it's in the vibrational area where it's just vibrating in the infrared, or if that energy is high enough to dislodge electrons? That's why you want to know this formula and be able to have it on hand, so that if you were given an energy of a photon, you could figure out what wavelength it is and how that affects the molecule. Here's an example of a practice problem that I think might be asked, but I'm not sure because there are no practice problems that I can look at. There are a couple on the College Board website, the AP Classroom, that we have access to, but they're all multiple choice questions, and they do not want us using any of the multiple choice questions as review type problems. And so I looked at the multiple choice questions and I came up with my own short answer type question that might be something that you have to look at. But honestly, I have no idea what it's going to look like at this point, since I've never seen questions like these on the AP exam. And because the AP exam is so short this year, I don't even know if this topic will be even tested on, but I figured I better cover my bases because it's one of the learning objectives of the first 7 units of the course exam and description. But anyway, let's dig our nails into this problem here. What would happen to water if it absorbed a photon of electromagnetic radiation with an energy of 3.6 times 10 to the negative 29th joules? Now, remember, just on the last page, energy of a photon is equal to Planck's constant times the speed of light over the wavelength. And your plan should be figure out what wavelength of this electromagnetic energy will be associated with the energy that's in the problem and apply it to one of these 3 options, I guess one of these 4 options. So let's solve for wavelength. I'll take 3.6 times 10 to the negative 29th joules and set that equal to Planck's constant, which is 6.626 times 10 to the negative 34th joules times seconds, times the speed of light, which is 3 times 10 to the 8th meters per second, and the seconds cancel each other out, divided by the wavelength, which is going to be in meters. So we want to solve for wavelength, and you can do a fancy little switcheroo. It's essentially a cross multiply divide, but it's a shortcut where if you're solving for something in the denominator, just switch places with it across the equal sign. So wavelength is equal to 6.626 times 10 to the negative 34th joules times seconds times 3.0 times 10 to the 8th meters per second divided by 3.6 times 10 to the negative 29th joules. When I punch that into my calculator, I get 5,522 meters, or 5.5 times 10 to the third meters. Now we need to answer the question, what would happen to this water molecule? Well, since the wavelength is 5.5 times 10 to the third meters, when you look up here in the electromagnetic spectrum, anything that has a wavelength of greater than 10 to the negative first is in the radio frequency. And according to what we just learned, this will have no effect on the water molecule whatsoever. If the wavelength happened to fall between 10 to the negative first and 10 to the negative third, it would be microwave. And if it was between 10 to the negative third and 10 to the negative fifth, it would be infrared. But since it's a much, much larger wavelength, this would have no effect on this molecule whatsoever. Now, I would never expect you to memorize the electromagnetic spectrum. In fact, I would probably give you a picture that looks just like this on any quiz or test that we take that pertains to this particular topic. And I would suspect that the College Board would also give you an electromagnetic spectrum as a frame of reference when you're trying to decide what your calculated wavelength would do to a particular molecule, whether or not it rotates it in the microwave, makes it spin in the infrared, or promotes its electrons in the visible and ultraviolet range. Well, that takes care of this video lesson. Thanks for watching.